we talked about the probability of at least 1, right? And the question was always, well, what if it asks at least 2? Because we know that at least 1 was 1 minus the probability that none happen. But often, at least once a day, we got asked, or I got asked, what if it's less than 2? What if it's less than 3? Or what if it's greater than 3 out of 5? Do I have to think about all the different possibilities? And that's where our probability models come in. The calculator gives us shortcuts. And that is our chapter 17. So in order to use our probability models, the situation must be what's called a Bernoulli trial. Bernoulli was a mathematician. A Bernoulli trial has, so 3 things must be true in order for a probability situation to be a Bernoulli trial. The first is there's 2 distinct outcomes defined as success or failure. Now, rolling a die can be a Bernoulli trial, even though a die has 6 outcomes. If you're interested in just rolling a 3, then rolling a 3 is a success, and not rolling a 3 is a failure. Okay? Heads or tails, success, failure, depending on which one you want, right? If I want tails, then tails is success. Could you
do numbers like 1 and 2?
Yes. If you were like rolling a die, what's the probability of rolling a 1 and a 2? Yeah. So that would be success, and then everything else would be failure. Yes, absolutely. Or even an odd, right? And then talking about, like we did a basketball example back in chapter 11, right? A success is making it, right? But a success could also be missing it if the question asks what's the probability that she misses 4 out of 5, or at least 4 out of 5. Now that is a success to miss because that's what the question is asking you for. So success failure depends on the question, not like success being, oh yay, that's a good thing, but what the question is asking you to focus on, okay? There must be a fixed probability of success for each trial. Okay? So it can't be like our driver's license problem where the first attempt you had a 34% chance of passing the driver's test, but then on subsequent tests you had a 72% chance. That doesn't work in a binomial or geometric models because the probability of success changed. Okay, so the probability of success has to stay the same, and they must be independent from one trial to the next. If they are not, then your sample must be less than 10% of the population. We could talk about getting green M&Ms, and we're not going to be replacing it, so it's not independent, but the number of M&Ms in the world is so large that our little sample of 100 M&Ms is not changing the probability of getting a green. Okay. Oops. We have two probability models, geometric and binomial. The geometric probability, we've actually calculated these already. What's the probability that the 4th car I see is German? That means the first car is not German, the second car is not German, the third car is not German, but the 4th car is. That's geometric. What's the probability that the first person with type AB blood is the 3rd person to come in and donate? That's geometric. What's the probability that my first basket made is my 4th attempt? That means I missed, and I made it. Caleb. No, these aren't sequences in series, so there's not an arithmetic or an sequence. It's geometric and binomial. Yeah. So the probability of getting the first head on the 5th flip. That means I got failure, 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 and the last one is 1 success. Okay? You have 1 success with geometric probabilities. Now the expected value for a geometric probability model is 1 divided by the probability. 1 divided by p is your expected value for this model. And the standard deviation is the square root of q. Q is the probability of failure, and p is the probability of success, right? Q is just 1 minus p. If the probability of success is 0.3, then q is 0.7. Yeah? They have to add the 1. Okay, the probability model, or the equation for geometric, looks like this. If I want, say, 5 heads, right? My first head is on the 5th attempt. Okay, so my x is 5. I have q, which is the probability of not getting a head, 5 minus 1 times, 4 times, right? Because if my first head is on the 5th flip, that's no tails, 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 tails. 4 tails, and then 1 success. So it's the probability of failure to x minus 1 power, 1 less time, and then 1 success. Yes?
So what represents successful?
Whatever the problem is asking for. If we're talking about flipping a heads, then heads is a success. If the problem says, what's the probability that your first tails is on the 4th attempt? Now tails is my success. Okay? If the problem says, what's the probability that she misses her first shot on her 5th attempt? That means missing the shot is actually the success, because it's what the problem asked for. Because that means she made the first 4. That would be 1 minus the probability of missing it. And then 1 time she misses it on that 5th attempt. Okay? So this is just a shortcut to the, let's say the probability of a missing a shot is 0.3. So the first miss is her 5th shot. Well, that would be 0.7, 0.7, 0.7, 0.7. She makes it 4 times, right? And she misses it on the last try, which is 0.7 to the 4th times 0.3. Right? This is 5 minus 1. So it's a shortcut to having to write it all out. Okay? And eventually we'll get to the point where we can plug the x and the probability into the calculator, and it spits out an answer for us. Okay? So x is the number of successes. So binomial is a situation where you have a fixed number of trials. Right? It's that simulation we did where what's the probability she makes 3 out of 5. And we did 5 shots and counted how many times she made the basket. Right? So what's the probability that this basketball player who has a shot percentage of 0.7 makes 3 out of 5 attempts? A fixed number of trials. Now what if it says 3 or more, at least 3? Then we'd have to add 3 plus 4 plus 5, right? At least 3 is 3 or more. So we'd have to add up the probability of 3 plus the probability of 4 plus the probability of 5. We have a fixed number of successes, and we have getting exactly a number or at least or less than that number, and our calculator is going to help us out with all of this stuff. The mean for the binomial model is the number of trials times the probability. That should make a little bit of sense. If I'm tossing a coin 10 times, how many heads do I expect? 50%, which is how many out of 10? 5, right? We got that by saying, well, 50% of 10 is 5. That's our binomial probability. N times P, the number of trials times the probability of success. The standard deviation is the square root of N times P times Q. Okay? Good news, these formulas are on your formula sheet for the AP exam. Okay? Your geometric and binomial means and standard deviations and formulas are on your formula sheet. Now, Most of you didn't get to probability with Algebra 2 because we don't do it anymore. It's like back in geometry, and I don't know whether they get to it or not. So we have this thing called combinations. Yes. Okay, so we have these combinations. It's like, how many different ways can you get 3 shots out of 5? It could be my first 3 shots. I could make one, miss one, make one, miss one, right? It's like, how many different combinations or how many different orders can you put your 10 songs on a playlist, right? You can order them. How many different ways can you order those 10 songs on a playlist? That the exclamation point means like 5 exclamation point is 5 factorial. That means 5 times 4 times 3 times 2 times 1.
Does that find other combinations or no?
Yes, is n times n minus 1 times n minus 2. So 5 factorial is 5 times 4 times 3 times 2 times 1. And I'll teach you a little bit about this just because you didn't probably learn it. Okay? So if I'm talking about, let's just say I have 5 songs. Okay? I have my 5 favorite songs that I want to put on a playlist. And I want to pick the order. Or how many different combinations could the shuffle function spit out for me? Right? Well, for the first song, there's 5 choices, right? There's 5 choices that the shuffle function can play those 5 songs. Now, one song is chosen. How many different songs can it choose for the second song? 4. How many songs for the third song? How many songs for the fourth song? And then they've used all of your 4 songs. There's only 1 left for the 5th song. That's how many different ways shuffle could replay that 5 songs in a playlist. My husband does that. So on Friday we talked about what factorial meant. It meant 5 times 4 times 3 times 2 times 1 if it was 5 factorial. This NCX, in your calculator it's NCR, and it means 5 choose 3, say. You have 5 sweaters and you are packing for a 3-day trip. If you're not like most women and pack all 5 so you have choices, you're going to pick 3 of your 5 to put into your suitcase. How many different combinations of those 3 sweaters could you have? That is what NCX means. This is the formula for it. You don't really need to use the formula. It's done in your calculator. It is usually written like this in statistics. It's written like this is your calculator. It's math, probability, NCR. N is the trials, and R is the number of successes. So 5 choose 4 is the number of ways you can have 4 successes out of 5 trials. Okay. 6 C2 is the number of ways you can have 2 successes in 6 trials. Okay. In the end, we're not going to use the formulas by hand, but again, on your multiple choice part of the exam, they love to say which one is the correct formula with the numbers plugged in correctly to see if you actually know what the formulas are and how they should be used. So even though we're going to use the calculator to do most of our calculations, and not even the NCR part of the calculator, we have a binomial and a geometric function in the calculator. We have to know what the formulas are so that we can use them properly. So the formula for your binomials, let's say I want 5, right? I have 5 trials, and I want 2 successes. The probability of success is p, and I have 2 successes, so it's p to the 2nd power. And then if I have 2 successes out of 5 trials, that means I have 3 failures, right? 5 minus 2 is 3. And so it's the number of the probability of failure to the number of failures. your exponents will always add to the number of trials. We can use the normal model to estimate the binomial model if this success-failure condition is met, meaning if we can approximate the normal model to a binomial distribution if we expect at least 10 successes and 10 failures. The number of successes we expect is n times p. If that's greater than or equal to 10, and the number of failures we expect is n times q, if that's greater than or equal to 10, then we can use the normal model instead of the binomial model. And that's sometimes easier to use when I want a cumulative probability. This condition becomes super important when we get to chapters 18 through 22. It's one of our conditions for the hypothesis test. All right, so now we get to examples. Okay, a new sales gimmick has 30% of M&Ms covered with speckles. These groovy candies are mixed randomly with the normal candies as they are put into the bags for distribution and sale. You buy a bag and remove candies one at a time looking for the speckles. Okay? This is a Bernoulli trial because we have success-failure. We either got a speckled M&M or not. The probability is fixed. 30% of all M&Ms are speckled. And it's independent because our sample is going to be less than 10% of all M&Ms in the world. Okay? If we were only looking at our bag, then it wouldn't be independent. So what is the probability that the first speckled one we see is the fourth candy we get from the bag? So the first thing and the hardest thing usually in this chapter is determining whether it's geometric or binomial. Geometric is one success on a specified trial, the last trial. So you have a bunch of failures and one trial at the end, or one success at the end. Binomial is you have a set number of trials. I'm going to pick out 5 M&Ms. I'm going to pick 10 M&Ms. What's the probability I get a certain number of speckled M&Ms in that 10? So binomial has a set number of trials. It's like 3 out of 5, 4 out of 6. And geometric is the first success is on this trial. So what situation am I looking at? The first speckled one we see is the fourth candy we get from the bag. Geometric, right? So this is geometric. My probability is 0.3. That's how I defined my model. So I want to write that. That's really important because it becomes one of the ways we're allowed to use the calculator shortcuts is by defining our model for the question. So we said this was geometric. This was one we could kind of do without the model, right? It was failure, 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 3 failures. And on the fourth candy, yay, we got the speckled one. So that was what's the probability of failure? 0.7 to the third times 0.3. There's a 0.7 chance I don't get a groovy M&M, and I have 3 of those in a row, and on the fourth try I do get the groovy M&M. That probability is 0.3. And so in my calculator, to the third times 0.3, which is 0.1029. Good morning. Thank you. Okay, what is our formula? What are the numbers set up? Not the final answer. 0.7 to the 9th, right? Times 0.3. If my first speckled candy is on the 10th, then I have 9 failures before my first success. So 0.7 to the 9th times 0.3 is 0.0121. Now, what's the probability we find the first speckled one among the first three we look at? And that little g is a hint to me, because as I do this once a year, I tend to forget what model I'm using. This is still geometric. The first speckled one is among the first three we looked at. So we're talking about it being ordered. With the binomial model, the order doesn't matter. I want one within the first three, right? So I found one speckled candy out of three. This is talking about the first one is either the first candy, or I find my first speckled one on the second one, or I find my first speckled one on the third one. So this is a cumulative. I'm going to add these up. So it's a probability that the first speckled candy is the first one, plus the probability that the first speckled candy I get is the second, plus the probability that the first speckled candy I get is the third, which is 0.3, right? What's the probability that the first candy I get is speckled? 0.3, right? How do I find the probability that the second one is speckled? No. The first one is not speckled, so 0.7. And the second one is speckled times 0.3. Geometric is ordered. The order in which you find them matters. Okay? And then what's the probability that the third one I get is the first speckled? Right. 0.7 times 0.7, or 0.7 squared times 0.3. So now we'll do that in the calculator. 0.3 plus 0.7 times 0.3 plus 0.7 squared times 0.3. And I get 0.657. And the last question here is, how many do we expect to check on average to find a speckled one? Expect and average tell us what? Those are two words that clue us to the mean. And the mean of the geometric model is 1 divided by the probability of success, which is 1 over 0.3, which is 3.33. So when it says how many do we expect on average, that means find the mean for this situation, for this distribution. Yes. Yes, 1 will always be on top. It's always 1 over p. And we're almost never asked for the standard deviation of the geometric model. But that formula is on the formula sheet. Okay, so if you ever required, like asked for that, reference the formula sheet. Okay. Okay, questions on that. Now, what's the probability that we'll find 2 speckled ones in a handful of 5? So you reach in the bag, you pull out 5 M&Ms. What's the probability that 2 of them are speckled? This is binomial, right? I have a fixed number of trials. So this is binomial with a probability, no, the number of trials is 5 and the probability is 0.3. So we write NP. Remember how we used to write N mu comma sigma to kind of abbreviate the model and the parameters, the mean and the standard deviation? We'd say the normal model has a mean of 26 and a standard deviation of 3. We'd write N 26, 3. And that defined the model we're using. Well, for binomial, we write the number of trials, comma, the probability, and that defines the model we're using. Okay? Once we've defined that model, that tells the grader of our AP exam that we understand the model we're using, what the parameters are, and then we can use the calculator commands, which we're not going to do yet, because we have to know the formulas, right, and what they are and how to use them before we can use the calculator commands as shortcuts. Okay, So what is the probability we find 2 speckled ones in a handful of 5 candies? So n is 5 and x is 2. So it's 5, choose 2. That's how we say that, 5, choose 2. There's lots of different arrangements where I could get 2 candies out of 5, right? It could be the first and the second. It could be the first and the third. It could be the first and the fourth, right? There's several different combinations in which the order I get those can be 2 out of 5. Times the probability of success, which is what? 0.3. To the number of successes power, what are my number of successes? 2 successes. And then probability of failure, 0.7. How many failures are there? 3. Okay. So probability of success to how many successes, probability of failure to how many failures. If I have 5 total and 2 successes, that means there's 3 failures. Okay. In the calculator, hold on. How do we plug this in? Okay. In my calculator, we're going to go math. So we're going to hit math. We're going to go to probability. And we're going to go to NCR. And then it gives us 2 little blank boxes. Okay, so we're going to put 5 in our first box and 2 in our second box. And I'm just going to hit enter so we see what that number is. 10. That means there's 10 different ways to get 2 speckled candies in a handful of 5. Okay, 10 different ways. So now it's 10 times 0.3 to the second times 0.7, oops, to the third. Hold on. 0.7 to the third. Okay. Now I don't have to hit enter after the NCR. I could just type in the 0.3 squared times 0.7, but I wanted you to see what that number is. 0.3087 is my final answer. So this is 0.3087, sorry. So that's not too bad, right? It kind of makes sense. It should. The difference is we really want to act like it's just this part of the equation, but we have to take into account the different ways we could order them. Although the order doesn't matter, so that means we're going to talk about all the different ways. If I only did this, it would be one way to get 3 failures and 2 successes. So the second question is now, what's the probability we find at least 2 speckled ones in a handful of 5 candies? So this was the question we had in chapter 14 when we talked about the probability of at least 1, and inevitably, well, what if it's at least 2? I said, we'll get there, right? Here we are. What's the probability of at least 2 speckled ones in a handful of 5 candies? So what are those options? What? It's more than just 1 minus none, though, because 1 minus none will give me at least 1. So let's talk about what this means, okay? The probability that x is greater than or equal to 2. That's at least, right? So that is the probability of 2 out of 5 plus the probability of 3 of 5 plus the probability 4 out of 5 plus the probability of 5 of 5, right? So I would have to find all those and add them up, which I can do, which we probably don't want to do, right? That's a lot. Ava.
Well, we have to do like probability at least 3, and then if that would be the case, we would just start at 3 or 5.
Correct. The question was, what if it asked at least 3? Then I would just be adding 3, 4, and 5. Okay? So this goes back to the idea that the probability for this whole thing is 0 of 5 plus a probability of 1 of 5. These are all the possibilities in this situation. 5 M&Ms, how many of them are groovy or speckled? Plus a probability of 2 of 5 plus a probability of 3 of 5. I'm just going to save some time. And that's all going to add to what? 1, right? When I wanted the probability of at least 1 was 1 or more, right? So we only had to subtract off the probability of 0, right? Which was easy. It's an easy calculation. That's why it was so nice. But if I want the probability of 2 or more, I need to subtract what off of 1? Right? So the probability that x is greater than or equal to 2, that's this part, right? This is the probability that x is less than or equal to 1, right? Do you agree with that? The 0 and 1 is less than or equal to 1. So the probability that x is greater than or equal to 2 is 1 minus the probability, I'll do this in blue, that x is less than or equal to 1. I want to keep 2, 3, 4, and 5. So that means I have to subtract off the 0 and the 1. Why is that a good thing? Well, the first is it's only 2 to calculate instead of 4, right? Because the binomial theorem equation's not that small. And the other thing is the calculator shortcut only does the less than part. Our calculator shortcut does not do a number greater than. So you always have to do, if I want greater than or at least, I have to do 1 minus less than that. Okay, so to use our shortcuts, we have to understand this concept. The complement. The complement of greater than or equal to 2 is 0 and 1, which is less than or equal to 1, right? If I actually included 2 in what I'm subtracting, I'm including that, so I'm actually only getting 3, 4, and 5 in my answer. Does that make sense? This is usually the part that messes people up, because when we do it, we have to change. We want greater than 2, we have to realize I have to do less than 1. If I want greater than 3, I have to do 1 minus less than 2. If I want greater than 4, I have to do 1 minus less than 3. So that I'm including the 4 in my answer. I'm including the 3 in my answer. Okay, so I could do this by the long way. I just set up the long way for you so we can appreciate the shortcut. 5, choose 2. 0.3 squared, 0.7 cubed. 5, choose 3. 0.3 to what? To the third. 0.7 squared. 5, choose 4. 0.3 to the fourth. 0.7 to the first. And 5, choose 5. 0.3 to the fifth. 0.7 to the 0. That is what I would have to do 2, 3, 4, and 5 and add it all up, and I have to plug all that in my calculator. Which is doable, right? It's not terrible. We'll answer this question at the end. But now if I do 1 minus less than or equal to 1, then I only have to do 5, choose 0, 0.3 to the 0, 0.7 to the 5th, plus 5 choose 1, 0.3 to the 1, 0.7 to the 4th. Less work, right? Less stuff to type in the calculator, therefore less chances to make a mistake with typing something into the calculator. Okay. So let's calculate that. Let's put it in our calculator. I'm going to do the 1 minus at the end, right? So I don't make any mistakes with parentheses and that. I'd have to have lots of extra parentheses here. So I feel like it doesn't focus. Oh, it's close enough. Is it recording? I can't tell. No. All right. Okay, so we're going to do the 0. So math over to probability down to NCR. We're not going to use NPR in this class. Okay? It is done in probability classes, but not this one. So 5 choose 0 is actually 5. There's only one way to get 0 out of 5, right? And then times 0.3 to the 0. Do I need to type in 0.3 to the 0? I'm going to insert a time symbol here, just in case. What's 0.3 to the 0? 1. So that's kind of not necessary. Times 0.7 to the 5th. And then I can do plus, math, probability, and CR again, 5, choose 1, times 0.3 times 0.7 to the 4th. I don't really need to type in 0.3 to the 1 power, right? It's just 0.3. And then I can hit enter. Then I can do 1 minus that. 0.47178. Okay. Now, here's some good news. You jest. If you have everything plugged in to the formula like this correctly, but you make a calculator error, they will still give you credit on the AP exam. Because you showed the most important thing, that you know how it goes into the formulas. So you made a little mistake entering it into the calculator. They give grace with that on the AP Stats exam. They're like, okay, well, it's all plugged in correctly, so they knew what they were doing, right? And then there's no double jeopardy. So if you had to use that wrong answer again, you don't get marked off on part B because you plugged it into the calculator incorrectly and got a number that was off a little bit for part C, or for B and C. So that's the nice thing about our exam. Calculus is much more like, nope, yep, you got to get the right answer because it's algebra based. We're more conceptual and analyzing. Okay, so I have a lot of writing, but in here we have this question. How many do we expect on average to find in a handful of 10? Expect on average tells us we want to find what? The mean. So the mean is n times p, which you cannot see. Mu is the number of trials times the probability. It says how many should we expect in a handful of 10? Okay, this should make sense. If 30% are speckled and I have 10, how many should I expect? 3, right? 10 times 0.33. Okay. I'm only highlighting that because it's in the midst of all of the other work that I put down there. Okay. Back when we talked about simulations, I said to you, how many heads would it take to convince you that a coin was not fair, right? And we had all these crazy numbers, 90 heads, but we realized when we did a simulation, nobody's simulation really got more than 65 heads out of 100, right? And that's because how many heads do we expect out of 100 coin tosses? 50. We expect 50. 100 times the probability 0.5. The standard deviation of that is n times p times q, which is 100 times 0.5, probability of heads, times 0.5, probability of a tails, which is the square root of 25, which is 5. So 60 to 65 is 2 to 3 standard deviations from the mean, which is really unlikely based on our normal model. Our success-failure condition meets. We expect 50 failures and 50 successes. So we could actually look at that as a normal model example instead of using the binomial model. That's why when we did a simulation, we barely got numbers above 65 and below 40 or 35 because we really expect 50 with a standard deviation of 5. So anything above 10, 60, and above or below 40 is more than 2 standard deviations from the mean, which is not very likely. Right? So this is how we can then use the normal model to make predictions as well, and we'll do some examples of that. Now, we have 3 probability models that we've looked at so far. The normal model that had 2 parameters, the mean and the standard deviation. And in the calculator, it was normal CDF, and you would put your lower bound and your upper bound. We have the geometric model. Has 1 parameter, the probability. The calculator commands are geomet PDF and geomet CDF. And you plug in the probability and the number of successes. Okay, remember, x is the number of successes. And the binomial model has 2 parameters, the number of trials and the probability. And it has 2 commands in the calculator, normal PDF and normal CDF. And you plug in the number of trials, the probability, and the number of successes you're interested in. What's the difference between PDF and CDF? PDF stands for point density function, which means a single value. In the normal model, because you're talking about the area under the curve, you cannot find a point because there's no area at one number. There's area less than it or above it. But with the geometric and binomial, you can find the probability of the first success being the 5th try, a single point, or you can find the probability that it's among the first 5, which would be cumulative, meaning it's adding it up. CDF stands for cumulative density function, right? Your cumulative GPA adds up your GPA for the entirety of your high school career, right? You have a single semester GPA, right? That's a point, a single semester, 1 value, but you also have a cumulative GPA that adds up all 4 years. So cumulative means you're adding them all up. So whenever I have an at least, at most, more than, less than, among the first 3, I'm using the CDF calculator command to add those all up, which is good news, right? Because that means I don't have to do the 0 and the 1 and put that in the calculator. I can use one calculator command to add up 0 and 1. The calculator does not do greater than in these two functions. Geomet and Binomial only do less than the x value you give it. So if I want greater than 2, I have to plug in less than 1. Okay? So that's where we have this right here. No. Don't like that. This right here. Still don't like that. I did it again. The Binomial PDF, if I want greater than, I do 1 minus the trial I'm interested in. We had just talked about that, right? If I want 3 or more, I have to do 1 minus 2 or less, right? If I wanted 4 or more, this allows us to do large ones too. What if I'm talking about more than 4 out of 20? Or more than 10 out of 20? Do I really want to write out that formula 10 times? No, we want to use the calculator. So if I want more than 10 out of 20, I'm going to ask it for less than 9, right? I have to change that to 1 less, otherwise I'm not including that last number in my value. So the calculator only calculates the less thans, 0 to the x that you give it. Okay. So here's another example from our textbook. This is probably not number 9 anymore. Actually, it is. Okay. A basketball player has made 80% of his foul shots during the season. Assuming the shots are independent, find the probability that in tonight's game he misses the first time on his 5th attempt, makes his first basket on his 4th shot, makes his first basket in one of his first 3 shots. What model is this asking us about? Is it geometric or binomial? Geometric. First basket, first basket, first basket. Geometric always has some order attached to it. So, how do I find that probability? What's the probability that his first basket is on his 5th attempt? Or no, his first miss. So the probability of a miss is 0.2. Here's an example when the success is actually a failure in life, right? We're talking about his first miss being the success. So that's our P. Our Q is the 0.8. So it's 0.8 to what power? To the 4th times 0.2. Because it's his first miss, not his first make. He makes 80% of them. He misses 20%. So he's going to make the first 4 shots, and the first miss is his 5th shot. How is the second question different? Say that louder. It's still geometric, but what are we interested? Is our success a make or a miss now? It's a make, right? So P is 0.8 in this case. So he makes his first basket on his 4th shot. Yes. So this is the 0.2 to the 3rd times 0.8. Because he misses, 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 and then makes it. .8 to the 4th and times 0.2. So this is 0.08192 and 0.2 to the 3rd times 0.8. If you want to get your cursor out of the exponent, you just push the arrow over button and it moves it down so that when you type times, it's not in the exponent. Isidro?
So we wouldn't round? Like
I don't round if the calculator is not, like, my calculator stops at 0.08192, so I just write the whole thing down. If the calculator is like goes on forever, then I round. Okay. And then makes his first basket on one of his first 3 shots. That means his first basket is his first shot. So that's 0.8. Or he misses and his first basket is on his second shot. 0.2 times 0.8. Or he misses the first 2, 0.2 squared, and his first basket is on his third shot. Okay? I want to make sure you use formulas tonight before you start using the calculator shortcuts. Okay? Because, like I said, it will have a question like this, and all of the multiple choice possibilities are different formulas. It'll have the binomial formula with the numbers plugged in. It'll have this with the numbers reversed, the 0.8 and the 0.2 reversed. And you have to pick the right work, not just the right answer. Okay? So we need to know that.